real exam questions. This is question 18 about shear force in beams. Determine the maximum shear capacity without taking into account the necessary increase in tensile reinforcement in the longitudinal direction. And determine the maximum shear capacity of this section, total height of 600 millimeters by 300 millimeters. The tension reinforcement is 3 diameters of 32 millimeters. Stirrups are diameter 12 center to center, 150 millimeters. 2 legs. And the compression reinforcement is 2 diameters, 25. Concrete quality is 25 megapascal. The characteristic value of the yield strength of the steel is 500 megapascal, and the concrete cover is 40 millimeter. First, we calculate the maximum allowable shear force in the beam due to the compression field. This is equal to this equation with cotangles theta, the angle of the compression strut, and cotangles alpha is the angle of the stirrup. But because the stirrup angle is vertical, it's 90 degrees, so cotangles theta is 0. In this equation, you see Z, and Z is taken as 0.9 times D, and D is the effective depth, and this is the total depth minus the point of gravity of the tensile reinforcement. So this is the diameter divided by 2 minus the stirrup minus the concrete cover. So in total gives you D 532 millimeters. Nu is the coefficient for the threads, and to reduce FCD, the concrete compressive strength, you multiply it by nu, and nu is equal to this expression and gives you for FCK equals to 25, 0.54. FCD, the design value of the compressive strength of the concrete. Just notice that alpha CC is according to the Belgium annex 0.85, but only for bending and normal force. For shear force, alpha CC is 1. So FCD is 16.67. Z, like we said, is 0.9D, and the cotangles theta is 2. So we take the smallest angle of the strut to have the minimum amount of stirrups for this angle. Cotangles alpha is 0 because you have vertical stirrups. Now we can fill in all the necessary parameters, and we arrive at 517 kilonewton. Resistance against shear force only by the concrete is given by the area of the concrete section multiplied by shear stress. The coefficient CRDC is a material factor and gamma C is 1.5, so CRDC is 0.12. Sigma CP is the normal force, external normal force on section, which is in our case 0. Rho L is the longitudinal reinforcement that is sufficiently anchored in the zone of where we are calculating the resistance of the shear force. It's 2,413 square millimeter divided by 300 divided by 532. The K factor is a scale factor. D is a millimeter, so this is 1.6131. The minimum value of the resistance to the shear force of the concrete alone is given by this formula, and we can fill in the different parameters, and we find min is 0.3585. So the total minimum shear force is then equal to 57 kilonewton. Now we start from those two formulas. The RDC, we have calculated each parameter in it, and then you see we have 104 kilonewton. So we take the maximum of those two and we arrive at 104 kilonewton. Then we are looking at the resistance of the stirrups, the resistance to the shear force due by the stirrups. So we take cotangles theta 2, means the smallest angle. VRDS, so the resistance of the stirrups to shear force, is then given by this formula. The stirrups is then equal to the area of two legs of the stirrups divided by the center to center distance, which is 150 millimeters, gives you 1.508. Z is 0.9 times the effective depth, the rest we know, and we arrive at 628 kilonewton. Now, notice that VRDS, the resistance to resistance of the shear force delivered by the stirrups, 628, is much larger than the one delivered by the concrete alone. But VRD max, which is the maximum allowable shear force that the compression field of the section can carry, so the struts can carry. So you will have strut failure at 517 kilonewton, but the stirrups, they can take up 628. So something is wrong here. Not wrong, but we should adapt. So we should adapt the cotangles theta in such a way that VRD max is, or in such a way that VRDS is at least equal or bigger to VRD max. So in this example, cotangles theta 2, VRD is of course the maximum of VRDC and VRDS, which is 104 and 628. And from this, take the minimum with VRD max, and we have 517 as the resistance to shear force, depending on the angle of the shear strut. So because VRDS is bigger than VRD max, like we said, cotangles theta should be optimized. VRDS, we've seen it in previous slide, is in fact function of cotangles theta, which was 2 in the previous calculation. And VRD max, the maximum allowable shear force that can occur without failing the compression struts or the compression field. We see that it is also depending on cotangles theta, so we have those two equations. So the maximum that we can get is when those two are equal. And when we make it equal, you get this equation. You multiply by cosinus theta quadrat plus 1. And you arrive at this equation for cotangles theta 0 has no meaning in our case. So cotangles theta here from this equation is then equal to 1.765, which is of course smaller than 2. So you have a larger angle, which makes the stress in the compression strut less. So the optimum value of cotangles theta is 1.765. We call this optimum because the maximum allowable shear stress is there at the same time that the compression struts are failing and the stirrups are failing. So it's a failure mode of the two at the same time. So that's why we call it optimum. And when you're using those formulas, you see it is indeed that it is the same. Now let's look at the parameter X, which is the dimensionless factor of the stirrup reinforcement. And you can make a graph from X in function of VRD max stirrup resistance, compression field resistance, and VRDS, the stirrup resistance. We know that this is coming from the stirrup resistance, and this is from the compression field. Now, if we take our first solution with cotangent theta 2, then x was 0.24, it's somewhere there, and cotangent theta 2, so it means that VRDS, this value here, is 0.49. That was the first solution that we had found, but you see clearly it is outside the maximum allowable values for the compression field. So now we will optimize the theta. So this stays the same, x stays the same, and we got 0.43. It's crossing the compression strut line, let's put it this way, at this point, and you take one straight line through it. So this is the new angle, the new cotangent theta, and this is the one for 1.7, cotangent theta equal to 1.7. So we summarize our answer. Its VRDC min was 57, VRDC was 104, so that's the allowable shear stress that can be taken by the concrete alone. Now we look at the angle of the compression strut, cotangent theta 2. The resistance for with cotangent theta 2 was 628, the resistance of the stirrups. The resistance of the compression strut was 517 kilonewton. So it means that the total resistance is the minimum of the two. So it's 517 kilonewton, which is the total shear resistance. Then we optimized, and for cotangent theta equals to 1.765, we have a resistance of the stirrups by 554 kilonewton. VRD max is 554. Of course, we are the same because it's the optimization. And VRD is now the total resistance, the total shear resistance is 554 kilonewton. So you see, by optimizing cotangent theta, you gain something like 10% in the total shear resistance.